Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Scanning Probe Microscopy, that is STM and AFM, from the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the basic components of a scanning probe microscope, that is SPM, are described. Then the various types of SPM, scanning tunneling microscope, STM, and atomic force microscope, that is AFM, are discussed. In this module, the electron tunneling through a potential barrier in STM is described in detail along with the advantages and disadvantages of STM. Then, the principle of operation and modes of AFM are studied and its advantages and disadvantages are discussed. Scanning probe microscopy, which was discovered in early 1980s when it splendid the world by producing the first real space images of surfaces with an unprecedented resolution of atomic scale. Presently, SPM is one of the most employed techniques in various disciplines, which include fundamental surface science, routine examinations of the surface roughness, and three-dimensional imaging from the atoms of silicon to microscale projections on the surface of a living cell. SPM belongs to the branch of microscopy which produce high definition images of a surface using a physical probes that scan the sample. This is done by keeping the probe stationary and moving the sample or vice versa. The collected data and its variation across the sample are employed to produce the sample's image. The resolution of such an image depends on the sample, the control that one has on the movement on the tip or sample, and the inherent nature of the data. Surface of solids can be mapped showing the structure of crystalline surfaces, distribution of point defects, structural defects like steps, etc. Let us discuss the basic components of a scanning probe microscopy. The basic components of a scanning probe microscopy includes probe and a scanner. These are discussed in detail in the following sections. The first one is the probe. As the distance between two objects is decreased to very small values, a variety of interactions occur between them at atomic scale. These interactions form the basis of scanning probe microscopy. The probe is very sensitive towards these interactions and it is configured to detect them. In scanning probe microscopy, this probe is brought very close to the sample which is being imaged. The magnitude of the interaction between probe and sample depends on the distance between them. This gives an SPM the ability to precisely map the surface topography of a specimen. The second component, now it is important to discuss about the probe tips of SPM. The type of probe required depends upon the type of SPM which is being used. The probe of SPM is having a very sharp apex. The resolution of SPM is determined by the apex of the probe, such that the sharper the probe, better is the resolution. For many cantilevers-based SPMs, example AFM, the entire cantilever as well as the probe are produced via etching, most commonly from silicon nitride. The conductive probes for STM are usually constructed from platinum or iridium wire. Let us discuss about the scanner. A piezoelectric ceramic is used to provide the precise positioning control which is necessary for all the SPM scanners. The application of voltage causes a corresponding change in the geometry of the piezoelectric ceramic. This voltage in turn is proportional to the resulting mechanical movement. In SPM, this piezoelectric scanner undergoes controlled and predictable bending, expansion as well as contractions. Thus, the probe sample gap and the position of the probe both can be controlled via this scanner. SPM scans the sample surface in a raster fashion. To create an image, specific values depending upon the type and mode of SPM are recorded while the probe is rastered over the sample surface. A map is created from these values which produces the final image of the sample surface. Let us assume that P represents the interactions between the tip and the sample surface. P can be used in the feedback system, that is Fs, only if there exists a sharp and unique dependence of P on the gap between the tip and the sample. That is, P is equal to P, which is a function of C. Feedback system controls the distance between the tip and the sample surface. The feedback system in a scanning probe microscopy is schematically shown in figure 1. A default value is set for the parameter P such that P is equal to P0. The feedback system then maintains this value of P. As the gap between the tip and the sample varies, the value of P changes from its equilibrium value P0. The change in P or delta P is fed to the feedback system, which then amplifies it and feeds a piezo transducer, that is PT. PT in turn controls the gap between tip and sample. PT uses delta P to alter the gap between tip and sample, and it brings this gap to its initial value, making the differential signal delta P close to 0. As the tip is moved across the surface of sample, its topography alters the interaction parameter P. Feedback system responds by restoring the default value of tip sample separation, that is P is equal to P0 in real time. Thus, when tip reaches a point xy at the sample surface, the signal V of xy fed to the transducer is proportional to the departure of the sample surface from the ideal plane, that is xy, at z is equal to 0. As a result, v of xy can be used to map the sample surface, thereby obtaining the STM image. Apart from visualizing the surface of the sample, STM can also be used for determining various properties of the sample. These include mechanical, electrical, magnetic, optical, etc. We will now discuss the types of scanning probe microscopy. There are two forms of SPM. The first one is the scanning tunneling microscope, which is STM, and the second one is the atomic force microscope, which is the AFM. Let us first discuss about the scanning tunneling microscopes, that is STMs. STM was devised by Gerd Binning and Heinrich Rohrer in 1981 while working at IBM. They prepared the first instrument to produce atomic scale real space images of surfaces. They were awarded the Physics Nobel Prize for this work. The phenomena of electron tunneling is exploited to acquire an image of the sample surface. This utilizes the principle of vacuum tunneling. Here, the tunneling probe and its surface are brought near contact at small bias voltages. If two conductors are held close together, the wave functions can overlap. The electron wave functions at the Fermi level have a characteristic exponential inverse decay length, that is k, which is expressed as k is equal to square root of 8m5 by h. Here, m is the mass of electron and phi is the height of local tunneling barrier, which is also termed as average work function of the tip of the sample. The schematics of electron tunneling through potential barrier in SCM, along with the band diagram, is shown in figure 2. We will now discuss about the advantages of the STM. STMs provide a three-dimensional profile of the surface which allows examining multiple characteristics of the sample such as roughness, surface defects, etc. It also allows measurement of various properties of the samples such as electrical, mechanical, optical, etc. STMs are versatile and are operable under ultra-high vacuum or ambient conditions. The samples investigated can be solid, liquid, and gas. STM can be operated in a wide temperature range from 0 Kelvin to few hundred Celsius. Lateral resolutions of the order of 0.1 nanometer and depth resolution of 0.01 nanometer can be obtained using scanning tunneling microscopy. Another advantage of scanning tunneling microscopy is that atomic arrangement on the surface can be obtained by measuring the DOS of the surface atoms. Now, moving on to the disadvantages of STM. STMs are complex to operate effectively. It is highly specific technique which requires great skill and precision. Also, for carrying out scanning tunneling microscopy, the surface must be very stable and clean. All STMs, they require extreme vibration control as well as very sharp chips. Also, the equipment is highly sophisticated and is quite expensive. We will next discuss about atomic force microscopy, which is abbreviated as AFM. Unlike STM, an AFM monitors the forces of attraction and repulsion between the probe and the sample. Atomic force microscopy has the ability to measure force, image, as well as manipulate the sample. It uses a cantilever having a sharp tip that is probe which scans the specimen surface. To image the sample, the tip is raster scanned over the surface of the sample. As the tip moves, the forces between the tip and sample detect the cantilever as per Hooke's law. Additionally, these forces can also be used to change the sample's properties in a controlled manner. The tunneling current varies exponentially with the distance between tip and sample, such that for a change of an angstrom in the tip sample gap changes the tunneling current, such that for a change of an angstrom in the tip sample gap changes the tunneling current by an order of magnitude. This makes STM extremely sensitive towards any changes in tip sample gap. The sample surface can be imaged both vertically and horizontally with atomic scale resolution. The tunneling current I decays exponentially with the gap as modulus of as I a alpha v e raised to power minus square root of 8m phi by h2t, where d is the tip sample gap and phi is the work function of tip. The tunneling current is the result of the overlap of electronic wave function of the tip and the sample. In this device, a tip is brought closer to the specimen so that electrons can tunnel across the vacuum barrier. The position of the tip is adjusted by two piezoelectric scanners with X and Y control. The Z-axis position is continuously adjusted, taking the feedback from the tunneling current so that a constant tunneling current is maintained. The position of the Z-axis piezo therefore reproduces the surface of the material. The other mode of imaging is by modulating the tip at some frequency and measuring the resulting current modulation. STM allows the investigation of local structures. STM provides information on the local density of states. The density of states is the quantity of electrons which are existing at particular entry levels in a material. Keeping the tip sample preparation constant, a measure of change in current due to bias voltage can probe the local density of states of the specimen. The electrons can tunnel to states which are present in the sample or tip. When the tip is negatively biased, then the electrons from the tip tunnel from the occupied states of tip to the unoccupied states of specimen. Thus, the spatial resolution achieved by using these tips is an atomic scale. Figure shows the atomic resolution in a scanning tunneling microscope. Let us now discuss about the advantages of SPM. Firstly, the resolution of SPM is not restricted by diffraction and therefore it can be of the order of few picometers. Secondly, the interactions between the probe and the sample extends only across the tip atom or atoms involved in the interaction. Thirdly, this interaction can be employed in manipulating samples to produce nanostructures. Then, another important advantage is that vacuum is not required to examine the samples. Coming on to disadvantages of SPM, firstly, the chip selection is highly challenging. Then, the scan process is time consuming. Another disadvantage is that smaller images are produced. Also, it is not suitable to study solid-solid or liquid-liquid interfaces. Let us discuss the principle of atomic force microscopy. The atomic force microscopy uses a cantilever which is having a sharp tip or a probe at its edge. This probe scans the surface of the sample. As can be seen in the figure, as the tip comes into contact with the surface of the sample, the forces between the tip and the sample deflect the cantilever. Displacement of cantilever is gauged with reflection of a laser from the back of the cantilever and detected on a segmented photodetector. AFM can be used to measure various forces such as mechanical contact, van der Waals, electrostatic, magnetic forces, etc. The atomic force microscopy can be operated in several modes. The first one is the contact mode. In this mode, the tip is dragged across the sample surface and the surface topography is obtained via the cantilever deflection. The contact mode analysis is performed at a depth where the overall force is repulsive. The attractive and repulsive forces are shown in figure 5. Non-contact mode. The cantilever tip does not touch the surface of sample. The cantilever is made to oscillate near the resonant frequency and the amplitude of oscillation is kept at few nanometers. Measuring the distance between tip and sample at each XY value allows the scanning software to reconstruct the surface topographic of the sample. We will now discuss about the tapping mode. The tapping mode can be performed in gases and non-corrosive liquids. The cantilever is made to oscillate up and down near the resonance frequency. The amplitude of oscillations is usually of few to several nanometers. The interaction of forces which are acting on the cantilever as the tip comes close to the surface changes the oscillation amplitude of cantilever. The image is formed by picturing the force of intermittent contacts between the tip and the sample surface. By overcoming the limitations of both contact and non-contact mode measurement, tapping mode has become an important AFM technique. The lateral forces which damage the sample, thereby reducing the image resolution, are not applied. Thus, the tapping mode can be used for routine analysis of sample surfaces, which was earlier considered impossible with atomic force microscopy. So students, let us now summarize what we have learned in this module. The basic components of a scanning probe microscope, that is SPM, were described. The various types of SPM, scanning tunneling microscope and atomic force microscope, were discussed. The electron tunneling through a potential barrier in STM was described in detail along with the advantages and disadvantages of STM. Then, the principle of operation and modes of AFM were studied and its advantages and disadvantages were discussed. Thank you students for your attention.